Hello and welcome back to My Favorite People. We said the carbon of any carbonyl group, due to the fact that it's unsaturated, it can get involved in nucleophilic addition reaction. And we practiced this one by adding water molecule to it. We said we can replace a hydrogen, one of the hydrogen water by alkyl group. In that case, we will be dealing with alcohol, or we can actually use diol instead of using 2 mole from water or 2 mole from alcohol. And I'm going to go after them. And so this time I will practice nucleophilic addition of 2 mole alcohol to a carbonyl group, regardless of whether it's aldehyde or a ketone. And as you see, the reaction is happening in acidic condition, and the product will be acetal plus water molecule. And now we say the reaction is not that favored, and in order actually to increase the efficiency of the system based on Le Chatelier effect, if anything from the product side gets reduced or eliminated, in that case the reaction will move to the right side. So in order to push the reaction to the right side, I'm gonna use a dryer or anything that it can actually take water out of the system. And in that case, the reaction has to move to the right side. Now, the ketone or aldehyde is not going to give you acetal right away, and it's going to go through a couple of steps in order to give you the final product. The first step, regardless of what you are using, is going to be addition of 1 mole from alcohol to the carbonyl group. Now, if you are using aldehyde and you add an alcohol to it, you get hemiacetal. Okay, hemi means half. I'm going to highlight this term. Hemi means half acetal. Why half acetal? Because acetal has two from this group, OR. Okay, whether it's OR2 or OR1, and then right now we have only one of them. Okay, one technically ether group there, and that's the reason we call it hemiacetal. Well, acetal has 2 of those groups. Now, if you're using aldehyde, we call it hemiacetal. If it's a ketone, we call it hemiketal. And but you will see that they use the acetal term for both of them. And like whether it's aldehyde or like it's a ketone, still we call it acetal. Okay, and now we say the reaction is going to happen under acidic condition. Okay, why do I need to use acid, and what type of acid I can use? Use one acid that whenever it's losing H plus, it's not capable of behaving as a nucleophile, and so we're going to use acidic H that attached to a bulky group, and also it has a plenty of resonance structures. And because it can easily distribute that negative charge inside the system, it will not behave as a nucleophile. Okay, it will not behave as a nucleophile. That's not gonna happen. And same thing with like a sulfuric acid. And you can get this. If you take 1 and H plus from it, now you get -1 charge. Where can I put the -1 charge? I can put it on that oxygen, or maybe here. I can put it in this position, and also we said we have that position as well. So at least 3 positions are available for it. And because it keeps getting distributed, inside the molecule, the conjugate base cannot behave as a nucleophile, and that's the reason we tend like to use this type of acids. Okay, let's try to go through the mechanism and see why we have to use acid, and like when do we get hemiacetal or hemiketal. Okay, now I start with a ketone in the first step, because I'm running the reaction in acidic condition, and so I'm going to have excess of positive charge, or in acidic H, and because I do have acidic H, is going to go after oxygen, or oxygen is going to go after H, and so now we will have carbonyl that is a protonated, and because it's a protonated, the positive charge is going to get exaggerated, because you can draw oxygen as oxygen as an atom with 2 lone pairs attached to hydrogen from one side and to carbon another side, and that's going to leave you with a +1 charge instead of delta plus. Okay, and so this one is really thirsty of electron density. Is going to be looking for a nucleophile, and the nucleophile in this case it will be an alcohol. Any alcohol molecule, it can find this carbon and it will attack the electrophilic carbon. And so what do we get? After removing this hydrogen from the system, that's going to give us ether on one side, and also still we have OH attached to the same carbon. So we have ether and alcohol functional group at the same time attached to 1 carbon. If you're dealing with such a case, and then we say it's a hemiacetal. Okay, so hemiacetal, it has OH and ether group at the same time. And this one is not much stable. Okay, it can go, it can get involved in some chemical reactions, and one of it is like we can get rid of OH and replace it by another alcohol group. Remember, still the solution is acidic. That means the OH group, this OH group, because it has two lone pairs, it can share one of those lone pair with acidic H, and in order to turn OH, which is really bad leaving group, to H2O, which is a good leaving group. Why? Because the charge here is 0, while OH, the charge is -1. And so this one is a good leaving group, while this one is a bad leaving group. Okay, so we protonated OH in order to turn it to a good leaving group. And now, like that, I turn it to water, and like any nucleophile, it can kick the OH out of the system, and then like we can actually replace it by another alcohol molecule. But it's not going to happen, like it's not like nucleophile is coming to the system, it's kicking the water out of the system. Now we get some help actually from the ether molecule, ether functional group that we have, and the reason behind it is this OR, it has lone pair. Okay, it can share one of those lone pair with carbon, and if we share the lone pair with carbon, now we're gonna facilitate the fact of taking those two electrons by oxygen. And now we got kind of like a carbonyl group that's attached to R, and because we have a huge positive charge here, now any alcohol, it can attack that carbon, and it will give us the acetal at the end. Okay, now you might say, how come you added the H plus to OH, not the OR? Okay, if you add it to R, which can happen, okay, what do I get? I get hydrate, okay? And I can, not maybe just hydrate, like I can take this one out of the system. If I take this one out of the system, I'm going to facilitate actually recovering the entire, the starting compound. So if we remove this, we will have a carbon with a positive charge. That carbon is going to make a double bond with oxygen, and very soon it will leave H out of the system, or it will let it go, and it will give us this, which it can get converted to a starting compound. So yes, OH it can get, it can get protonated, but if that one happened, it will give us a starting compound. And so that's the reason I added to OH, not OR. But the main question I want to ask here, or I want to keep clicking on it, how come we are using only acidic condition, not basic condition? In case of hydrate, we said we can use acidic or basic. Let's go back for a second. And in case of hydrate, we said the reaction can happen in basic or acidic condition. In basic condition, as you see, OH was added to the system. We got this intermediate. Now that intermediate got an H from solvent, it turned to hydrate. So how come we can't have this for acetal? Okay, what's the problem with it? Okay, let's review some facts before answering this question. The first one is the OH versus RO minus. If you take an OH and you react it with an alcohol, let's say CH3OH, say we get an equilibrium and we get H2O plus CH3O minus. Okay, the pKa for this one is around 15.5, while pKa for water is around 14. So based on pKa, this reaction should not happen. Okay, that means OH cannot take this acidic H from alcohol. Okay, so this one is not going to happen. What does it mean? It means inside the aqueous solution, your nucleophile, it will be OH, not RO. Okay, so that means we can add, like technically alcohol group or like an ether, group to the carbonyl. That's not going to happen. And let's say we have equilibrium and we have a trace from this. Okay, so we have a trace from this one. Okay, let's see what will happen if we have a trace from it. So I go ROH. This one is going to react with the hemiacetal that we have, and we're supposed to kick OH out of the system. So the transition state is going to be something like this. Okay, what do we have here? Say we have R. This one can be hydrogen or R. And what do we have here? We have OR. Okay, and this one is supposed to be added. Okay, maybe I should bring it closer. This one, I'm going to bring it here, while OH is leaving the system. This one is a bad leaving group. Why? Because the charge is going to be -1, and then it's already attached to carbon. It doesn't want to lose that one. Okay. Next thing is this one is neutral, and you want oxygen to share lone pair with carbon. Okay. Now, if you do it, this one is going to get a +1 charge. Where is it? On oxygen. Okay. You want to take a neutral molecule and pair it with a carbon, and that's going to cause you to have a positive charge on oxygen in order to kick OH with a negative charge, which is really a bad leaving group. That's not really good things. Okay. And I said, how about having trace of this? What if you have a trace of this one? The problem is this species in basic solution is not that much stable. And because it's not that much stable, the second you generate it, very soon it will find water and it will take H from it. And because I don't have much from it, this transition state is not going to happen. So I'm going to say this one is really not much common. Okay. And so in this case, this one is -1. And because I can't have really such a transition state, this is not really realistic, transition state, I'm going to say the reaction will happen only in acidic condition. Okay. So the reaction is happening in acidic condition. Now, if you run it in, with aldehyde, you will get, the product. Again, it's an acetal. You have 2 OR group attached to it plus water. And the same thing with ketone. And in the case of ketone, you will have these 2 substituents attached to the same carbon plus water. Now, for aldehyde, there is a chance to get acetal, and the product will be the technically favored over the reactant. And while in case of ketone, it's not much, and starting compound, it will be the major one. Okay. And for aldehyde, you have to use really basic aldehyde. Why? Because the second you start replacing one of the hydrogen by alkyl group, you will have a steric effect. And that's the reason it says with really simple aldehyde. Simple aldehyde means you have only hydrogen. Okay. Or you have 1 hydrogen and 1 CH3, for example. Okay. And because the second you add, replace, 2 hydrogens or one of the hydrogen by really bulky group, you will have too much steric effect between hydrogen and that bulky group, and the reaction is going to get, is going to move actually backward. Okay. So let me summarize whatever I said until now. Now, if you use 2 mole from water molecules and you add them to a carbonyl group, you will get hydrate. And the hydrate is not that stable molecule. If you use 2 alcohol and you react them with a carbonyl group, you will get, forgive me, if you use 1 mole, my bad. If you use 1 mole from water and you add it to a carbonyl group, so if you use 1 mole from water and you add it to carbonyl group, you will get hydrate. And if you replace a water molecule by alcohol, and you will get hemi-acetal. But if you use 2 moles, so in this case, if you use 2 mole from alcohol, you can actually get acetal. Okay. Now, hydrate is not a stable molecule. Hemi-acetate, you can get it if it's a cyclic. If it's a cyclic molecule, yes, it's possible. And so that means always there is an equilibrium between the starting compound and the hydrate or hemi-acetal. In case of acetal, when you form the acetal, you're going to lose that equilibrium. And when you lose the equilibrium, that means in order to send it back to the starting compound, you need to play with the condition. You need to really dilute it and add a bit acid. Then the reaction is going to go backward. Otherwise, it stays as it is. And because it's stable enough, we can use it to protect carbonyl group in order to run another reaction on one side of the molecule. And that one is, we call it actually kind of like a protecting group. And that's going to be subject of another lecture. For now, thank you very much.